my name is Dana Golden. Today we're going to go through linear regression with NumPy and also sklearn. So we're going to start by importing our packages, and then we're going to try to run this. We have our x data, we have our y data. We can't create this. Why not? There's multicollinearity. So what we found is it's a singular matrix. So if you have a matrix that won't row reduce, a matrix that does not have full linear independence, you're not going to be able to run a linear regression. So let's fix that. So now we have a x variable that is not linearly dependent, and we get our outputs. So it's this beautiful function here, x transpose x to the -1, x transpose y. It's an analytical solution. You can also have a numerical solution, which is x beta minus y squared, and you do maximum likelihood on that. Gradient descent, we get our hypothesis function, which is np dot x and theta. We calculate the error, which is h minus y. Calculate the gradient, which is just x transposed and the error term, dot product of that, divided by m. And we calculate theta, which is calculated using gradient descent, where we adjust by the gradient just a little bit. Remember, this is the derivative, so we're trying to find the bottom. And then we calculate the cost function, and then we go back through over and over again. So now, in the regression, we're just going to add on a stack of ones to our x, and then we're going to calculate, and we're going to create our vector of thetas, and then we're going to use gradient descent to find our true thetas. So here we are, because it's linear regression, we have a cost function that converges very quickly. And here's what that looks like for the first variable, and here's what that looks like for the second variable. Very good fit, few data points, very quick. And then we have our betas. Now we're going to do the same with a regularization term. Recall that regularization is about stopping overfitting. So you have a bunch of different variables, and then you're going to penalize the variables for being large. So you have this penalty term on beta, so you have this cost function plus this penalty. Going to mechanically increase the cost function. So we create our starting betas based on linear regression, what we would get from linear regression, and then we add in our lambdas to penalize large coefficients and effectively make them go to 0. So this is how you choose different coefficients. So we've effectively forced this coefficient to, we've scaled each of the coefficients by how much they add. Now here's ridge. This is just a analytical ridge where we are just basically inverting x beta transpose to add x beta plus lambda times I. We can do a little bit better than that using optimization. So we're using basically just a lambda of 1 is the main change here. So lasso, we're using what's called the L2 norm. This is the L1 norm. So here lambda is squared, and here, here lambda is yeah, here lambda is, that's the problem. This is also lasso. The adjustments have not been made. So follow this for what ridge looks like. So this is ridge coefficients using regularization. You can just have lambda times I. Here, lambda is not squared. Here, lambda is squared, and that's the difference between ridge and lasso. Ridge scales coefficients. Lasso eliminates some coefficients and scales the others. The elastic net is in between ridge and lasso. So you have a lambda 1 and lambda 2. Lambda 1 is treated like a lasso coefficient. Lambda 2 is treated like a ridge. Coefficients there. Now we're going to do it with sklearn. So linear regression, linreg.fit x, y. We get the coefficients. Then we do with lasso. So we have slightly scaled coefficients. One goes to 0, one gets larger. And then ridge, they both kind of get a little bit smaller. The intercept, in particular, is also scaled. And then we do elastic net. Then now we're going to do an example with the California housing data set. Data frame of data, split it into x train, x test, y train, y test. We're going to scale it all. Then we're going to get linear regression, ridge, lasso, and elastic net. You get the model name, MSE, R squared, model coefficients. And here we go for that. As you can see, linear regression is very similar to ridge. Lasso has a significantly higher MSE and significantly lower R squared. That's because it's preventing overfitting. Same thing with elastic net. It's kind of in between ridge and lasso. Take the coefficients. Now we're going to plot how they're different. In this case, ridge and linear is the same. That's not true in general. It's true in this case. And the lasso coefficients are significantly smaller, whereas the elastic net coefficients are mostly in between ridge and elastic net. And some of the coefficients are zeroed out for lasso, as lasso is kind of designed to make the coefficients smaller and also zero some out. Thank you, and I hope you have a great day. This was linear regression.